Hi everyone. Let us continue our studying of various molecular geometries and trying to extract as much information as we can from those different shapes. And in this video, we're going to look at bond dipoles, or another way to say that is the polarity of a bond. Then we'll look at the net molecular dipole. And finally, we'll discuss how to determine whether a molecule is polar or nonpolar. All right, the first topic, bond dipoles, and we are going to use Pauling's electronegativity table. Now, eventually, or maybe even now, you may not need the electronegativity table. You should already know that fluorine is the most electronegative, number one, and oxygen is considered number two. Okay. Those are atoms that, when participating in bonding, like to pull electrons towards it. So we understand that a lot of the molecules that we've been looking at in our study of Lewis structures, for instance, let's say carbon with a hydrogen, fluorine, maybe we have an oxygen molecule like that, we understand that these are all covalent bonds. And covalent bonds, the two atoms of a bond are sharing those electrons. But the thing is, a lot of times those electrons are unequally shared. They spend more time closer to one atom than the other. And for instance, since fluorine is very electronegative compared to carbon, you would predict that there's a bond dipole in this direction. So that's one way to indicate an unequal sharing of bonding electrons. Another way to indicate this is using partial charges, partial negative, partial positive. Okay, so that's the symbol. This looks like a lowercase delta, partial negative, partial positive. There are cutoffs. What determines whether a covalent bond has unequal sharing or close to equal sharing or equal sharing? Well, using the Pauling electronegativity table, if the difference between the two atoms is 0 to 0.5, okay, you will consider that bond as a nonpolar covalent. Okay. And examples of that, are going to be something where an element is diatomic, because we have two of the same atoms, they have to equally share those two bonding electrons. Okay, so that's easy. That would be a bond dipole of 0. Okay. But what if we had, for instance, how about this, just a carbon-hydrogen bond? Okay, I know carbon would have other bonds, but just focusing on the carbon-hydrogen bond, carbon has 2.5 and hydrogen has 2.1, so that's a difference of 0.4. So this is nonpolar covalent as well, even though the atoms are different. Okay. Next, if the difference is between 0.5 to 2.0, then that's where you have what's called a polar covalent bond. Okay, and that's typically going to be a bond between an atom and one of the halogens. So, for instance, if we have boron bonded to any one of these 4 halogens, actually, well, maybe not iodine, but let's do boron and chlorine. Okay, the bond dipole is definitely going to chlorine, and the difference is 1.0. 1.0. So that falls into this range of polar covalent bond. Now, don't worry about the units of electronegativity, but we are going to talk about the units a little bit about bond dipoles. But let me take care of the last type of bond using Pauling electronegativity table, and that's if the difference is greater than 2.0, you have an ionic bond. And we know ionic bonds. Let's take, for instance, sodium chloride. You have Na plus and a Cl minus. Here we don't have a sharing of electrons. We actually have a transfer of electrons. If you draw the Lewis dot structure or Lewis dot symbol for each of these, you would have that. Sodium gave up its electron to chlorine. And when we take a look at the Pauling electronegativity table, chlorine is 3.0, sodium is 0.9. That's a difference of, 2, right? 2.1. So that's definitely greater than 2, so this is ionic. Now, in this unit, where we're learning about molecular geometry and intermolecular forces and bonding theories, we're mainly concerned with covalent bonds, nonpolar covalent and polar covalent. Okay, let us take a look at a molecule now, and we're going to talk about its bond dipoles, but then we're going to add up those bond dipoles to figure out whether it has a net molecular dipole. And two examples I want to go over first are going to be carbon dioxide, okay, and water. You notice that both have 3 atoms, right? But the bond dipoles and the molecular dipole, which we'll see in just a bit, are going to be different because it's based on the shape. Carbon dioxide is, the 3 atoms are in a linear shape. So I am drawing the Lewis structures kind of fast. Hopefully you've been practicing, and it's just as fast for you. It's linear. We talked about shapes in the previous video. It's linear, and you know that this angle is, well, I'm just going to put here linear. The angle is 180 degrees. But for water, water is actually, the molecular geometry is bent because you have these 2 lone pairs on the central atom. So this is bent. So even though they both have 3 atoms, the molecular dipole, the net dipole, is going to be pretty different. Now, let's talk about carbon dioxide. I'm going to try to keep consistent, and I'm going to use pink as what's called the bond dipoles, and maybe purple. Or should I use? I'll use green. Green. That's going to be the molecular dipole. Essentially, it's going to be the addition of all the bond dipoles. Okay. So here we have carbon and oxygen. Oxygen is more electronegative, so it's pulling electrons towards itself, and both oxygens are pulling electrons towards it, making carbon actually pretty partial positive. But I'm not going to clutter up the drawing by drawing my partial negatives and partial positives. Okay, we'll just rely on the bond dipole arrows. What about this molecular dipole? What you want to pretend, at least I like to pretend, is you have tug of war, and we have one person pulling in this direction to the left, and we have another person pulling to the right. Because they're equal pullers, because they're both oxygens, and because the geometry is linear, these tug of war, they balance out. The pull, the forces balance out, and we actually have a net zero molecular dipole. Net zero molecular dipole. Now, we're not going to worry too much about numbers, but molecular dipole can be measured and has a unit. And the units are, well, first of all, that U or what is that, mu. That is the symbol for molecular dipole. Okay. And it's going to equal some number, and the units are what's called a debye. And the debye, or big D, equals, it's a weird number. It's not an SI unit, but it's 3.336 times 10 to the 3 C dot M. So this is a charge, right? This is coulombs. And this is meters. So times length. I'm not worried for my class about the number, okay? I'm more worried whether we have a zero, just like carbon dioxide, because it says net zero, or if we have a non-zero, if there is a molecular dipole. So let's take a look at water. Before we take a look at water, here's my molecule for carbon dioxide. So you can imagine, as you're pulling to the left and pulling to the right, they're equal. Oops, don't break it. They're equal pull forces, and that carbon is not going to move in either way in this tug of war. But water is different. Here we have water, and I put the bunny ears, or the Mickey Mouse ears, because these represent the lone pairs, causing the bond to become bent, the bond angle to be bent and not linear. If we take a look at the bond dipoles in pink, oxygen is more electronegative, okay? It's the second most electronegative atom, and it's pulling electrons away from hydrogen. Okay. So if you take a look at this molecule, let's get rid of the lone pairs, because now we're just looking at tug of war. But look at the direction now. We have maybe this purple person pulling towards him, and we have this red person pulling towards her. Okay, so they're both pulling slightly up, but they're not pulling unequally in the x direction, in the horizontal direction. Okay, so yeah, you could do what's called vector addition. You could take a look at each of these bond dipoles. Okay, so we have this bond dipole going like that, and then we put this bond dipole at the end of that. Okay, so this is sort of like a vector addition. We started here, and we end up here. That's one way to do it, visually. And just line up your dipoles, and you notice that the net dipole is going this way. I said that our molecular dipole is going to be green. This is a net molecular dipole. The net molecular dipole is going up towards the oxygen, and it's going straight up. It's going straight up. Now, if I held it like this, it would be going straight to the right. Okay? So this is your net molecular dipole, and I did look up the number for this. The molecular dipole equals 1.85 debye. But again, I'm not interested in the number. What I'm interested is that you understand that this has a net molecular dipole and carbon dioxide does not. Carbon dioxide does not. The bond dipoles cancel. Okay. Bond dipoles cancel. And this one you get a net movement. They cancel, right? Because if I take a look at this arrow, and I superimpose this arrow, the beginning of this arrow to the end of this arrow, we end up at the beginning. No movement. The bond dipoles cancel out. Here they don't cancel out. Okay? So using these two simple examples, we're going to assign one as polar and one as nonpolar. If the bond dipoles totally cancel and you get a zero molecular dipole, that molecule you're going to know as nonpolar, and that's your conclusion. Carbon dioxide is nonpolar. But if there's a net dipole, then you're going to say the molecule is polar. There's an imbalance of bond dipoles. Okay, either based on the number, but really based on what's called a vector addition. Or just think of tug of war. When you have those two people pull, where do you think this red atom is going to go? It's going to go up, okay? Because you have two pullers, one on each side, but they're both pulling slightly upwards. Let us take another example. We'll do this a little bit quicker because I want to get also to some more complicated examples. This is going to be, again, pretty simple, but it's only simple if you know your geometries, your molecular geometries very, very well. I'm going to compare B, let's see, I had it written down. Let's do BF3 versus NF3. Interesting. Each has 4 atoms, but one is, we're going to have to assign polar or nonpolar, and they may be different. B boron, you should know, can have an incomplete octet. It is in group. It's called 3A, and it has 3 valence electrons. It is essential for us to understand that BF3 is trigonal planar. And again, that is the molecular geometry. If you're a little bit unsteady about molecular geometry, there are previous videos in this unit that talk about that. And this is trigonal planar. It looks like that. Flat. Now, if we take NF3, NF3 actually has a lone pair on the central atom. This is not in the same family as BF3. This is in the tetrahedral family. And I've talked about shape families in a previous video. Okay, it's tetrahedral because it has what I call 4 balloons. 4 balloons. And the model of that is this. So yes, one of the balloons is a lone pair, and it's pushing the 3 bonds towards each other. But this is also based on VSEPR rules, VS EPR. The molecular geometry for this is called Trigonal Pyramidal. Look at your tug of war now. Here are your bond dipoles. Fluorine is definitely pulling in this molecule, and here are your bond dipoles for NF3 as well. Not only would you want to be able to name the molecular geometry, okay, they're both, well, no, one is in the trigonal planar family, one is in the tetrahedral family. So tetrahedral meaning the shape made by the electron domains. But in terms of geometry, this is trigonal pyramidal. So here's your, well, let's do this one first. Can you imagine if you had a 3-person or 3-team tug of war? One pulling, let's hold it like this actually, one pulling to the left and 2 pulling to the right, but not with their full force because they're angled. If I hold it like this, okay, let's try to actually draw the bond dipoles. I have one bond dipole going here, okay. I have one bond dipole going here, okay, this one going to the northeast, and then this one going to the southeast. Do you see how I ended up in the same place? So again, you could do this mathematically using geometry, but it's just easier to just use inspection or to do vector addition in which you line up the different bond dipoles or all the bond dipoles and see if you end up anywhere different. You know, for this one, let's take a look at our molecule. Oh, by the way, so this is a bond dipole of 0. So dipole equals 0 dibi. And what is our conclusion when that happens? This is nonpolar. Okay, the bond dipoles cancel out. But if I take a look at this NF3 and I hold it like that, okay, it's pulling towards fluorine. And do you see how all of them are pointing down slightly? Okay, if I look at it straight on like this, all right, in this plane, the plane of the paper, that atom is not going to move because again, we have kind of this situation here, even though they're angled, okay? If I just look on straight at it. So if I hold it like this, that atom, that nitrogen atom, is not going to move in the x direction, but it's definitely going to move in the y direction because they're all pointing slightly down and there's no counterbalance. There's no counter going up. This one has a non-zero Debye and it is polar. The bond dipoles do not cancel out. And from our previous page, not cancel, from our previous page, we said that we're going to indicate the molecular dipole, or the net molecular dipole, with a green arrow. It is going definitely down. Okay, you could put it to the right, you could put it left. You know, you could even put it right here, right underneath. That's perfectly fine as well. Okay, but don't do both. All right. I like to put it off to the side, so it's not cluttering up the drawing. Okay. All right. Let's take a look at a couple more shapes, because what have we done so far? We've taken 4 shapes, basically. We've taken linear from the linear family, bent. What family is this again? This is a tetrahedral family because it has 4 balloons. This is 4 balloons as well, but now 3 atoms, so this is trigonal pyramidal, and we have trigonal planar. Let us look at all the shapes. And I have that over here. Remember this sheet? For each of these shapes, okay, if you assume that these white spheres are all the same atom, you know, you could pick fluorine, I would pick a halogen, okay, so it's easy to figure out the bond dipoles. Or you could actually use these examples here, right? We have chlorine, we have oxygen, so the outer atoms are still pretty electronegative. But anyway, for each of these, you could assign whether the molecule is going to be polar or nonpolar. So literally, PCl5, is that molecule going to be polar or nonpolar? Do the bond dipoles cancel out or not? Okay. Let me go through. I'm not going to draw this out for you. Okay, I'm not going to draw out the bond dipoles or the net molecular dipole. I'll just discuss it here. If this is PCl5, the bond dipoles cancel out. The up cancels the down for sure. And then this one straight to the left is canceled out by these two to the right that are at an angle. Okay, technically this is trigonal planar, these 3 atoms right here with the central atom. Okay, so this is nonpolar. Just like trigonal planar appears nonpolar. Okay, but when we remove a bond to a halogen, so now we only have SF4. Now do you see how there's no counterbalance, and we have 2 fluorine atoms pulling to the right slightly, but no counterbalance pulling to the left? Okay, so this is polar. T-shaped is polar. This linear is nonpolar because the up direction is being canceled out by the down direction. We have no pulling on the sides because these are just lone pairs. We don't have an atom that's electronegative. So again, you could do that for all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 shapes. Just beware. For instance, this carbon tetrabromide is nonpolar. But if I replace this bromine with a hydrogen, the carbon-hydrogen bond is not really polar, so we wouldn't expect a tug-of-war pulling upwards or downwards. We consider that a nonpolar bond between carbon and hydrogen. Okay? That means that these 3 bonds, the ones to bromine, the dipoles are pulling downward. So this molecule can be polar if we change one of these bromines into hydrogen. So you have to take a look also at the identity of the molecule, or the identity of the atoms around the central atom, not just the overall shape. Understood? Okay. So at the bottom, also assign polar and nonpolar. Okay. All right. That's all I want to say for this as a good practice. Now we're filling in the chart, right? We have angles, we have geometries, we have electron domain shapes, and now we have polar and nonpolar.